This question is from GATE Mechanical Engineering of 2019. This is question number 33 of set 1. The question is, a gas is heated in a duct as it flows over a resistance heater. Consider a 101 kilowatt electric heating system. The gas enters the heating section of the duct at 100 kilopascal and 27 degrees Celsius with a volume flow rate of 15 meter cube per second. If heat is lost from the gas in the duct to the surrounding at a rate of 51 kilowatt, the exit temperature of the gas is. Now we need to find the exit temperature of the gas from the duct, and also we need to assume that the pressure is constant, it is an ideal gas, and the change in kinetic and potential energy is negligible. And the value of Cp and R, that is the gas constant, is given in the problem. Now this is mostly a substitution based question. Steady state energy equation formula if you know, and if you know how to apply it, you can directly substitute the values and get the answer. You just need to take care of the values and you have to put it precisely. Otherwise most of the time we get the wrong answer just because of the calculation error. So let's write the steady flow energy equation. From the first law of thermodynamics, the steady flow energy equation can be written as, let's say there is a duct with as inlet. So this is the inlet, flow is going in the duct, and this is the exit. Let's say T2 is the state of exit. Now suppose there is an electric resistance heater. So this is the electric heater through which the gas will pass. Now because of this electric heater, work is done by the system. Also it is given in the problem that heat is lost, right? So let's write Q dot, the rate of heat loss. Now the steady flow energy equation can be written as the change of heat with the change in mass plus enthalpy at the inlet plus the kinetic energy of the gas at the inlet plus the potential energy. And that should be equal to work done per unit mass plus enthalpy at the exit plus kinetic energy at the exit plus the potential energy at the exit. So this is the steady flow energy equation. Now it is already mentioned in the problem that kinetic energy and the potential energy is neglected. This is because usually, or I can say mostly, the change in kinetic energy is negligible as compared to the enthalpy. It's very small. Okay, so let's ignore the kinetic energy and the potential energy here. So we can write the steady state energy equation as delta Q by delta M plus H1 is equal to delta W by delta M plus H2. Let this be equation number 1. Now according to the problem, we need to find the exit temperature. So T exit, or in this problem let's say T2. We need to find the value of T2. Now to find this T2, we will write the given information, that is the other thermodynamic properties that is given. So we are given the pressure at inlet, that is P1 is 100 kilopascal. The volume flow rate, let's write V1 dot is 15 meter cube per second. The inlet temperature is 27 degrees Celsius, and in Kelvin it will be 300 Kelvin because we add 273 plus 27, so we get 300. The value of gas constant for this problem is given as R is equal to 0.5 kilojoule per kg Kelvin. Also it is given in the problem that the gas behaves as ideal gas. So we have the ideal gas relation PV is equal to MRT. Now if you like, you can pause the video here and try to find the solution using this given information and the concept explained above. This is mostly substitution problem, so hopefully you'll be able to find the solution. Also, if you need any help, you can just resume the video. Let's continue with our solution. So in our problem, we don't know the mass flow rate. So let's write from the ideal gas equation, we can write P1 V1 should be equal to mass flow rate, that is m dot r into T, and this is volume flow rate. Okay. So from here we can write mass flow rate is equal to, because mass at the inlet and the exit will remain same from the conservation of mass, this m dot mass flow rate will be equal to P1 volume flow rate divided by R T1. This is T1, okay, at the inlet. So from here, if we substitute the values, that 100 kilopascal, pressure at the inlet is 100 kilopascal, the volume flow rate is 15 meter cube per second, divided by R value given is 0.5 kilojoule per kg Kelvin, and the temperature is 300 Kelvin. So from here we will get the mass flow rate to be m dot is equal to, if you can use the calculator here, you will get 10 kg per second. Now from equation 1, multiplying change in mass both side, we can write, or the mass flow rate both side, we can write from equation 1, let's write from equation 1, the energy equation can be written as Q dot plus m dot H1 is equal to work plus m dot mass flow rate into enthalpy at the exit. We know enthalpy H1 is equal to CpT1 and H2 at exit will be CpT2. So we can substitute here and we'll get, we can write this energy equation as Q dot heat flow plus m dot mass flow rate into Cp into T1 is equal to plus mass flow rate to Cp into T2. Now from this energy equation, we can we need to find the value of T2, right? So we can write T2 in terms of these equations as, so T2 will be equal to Q dot minus W dot plus m dot CpT1, and this mass flow rate into Cp will divide with it, so divided by m dot Cp. So this is the expression for T2 that we need to find. Now we can just directly substitute the value here. We will get Q dot value is already given in the question, and it will be minus 51 kilowatt minus the work done is also work done by the system. Here heat is lost, that's why the negative sign represent the heat is lost. So the work flow rate is, it's also given because of the heater, it's negative 101 because work is done by the system, kilowatt, plus mass flow rate we just calculated, it is 10 into Cp value is, it is mentioned in the problem, it is 1 kilojoule per kg Kelvin, and T1 is already given in the question, that is 300. This whole divided by the mass flow rate, that is 10 into 1. And if you do the calculation, you will get T2 is equal to 305 Kelvin. So we need to find in terms of degrees Celsius. So T2 will be equal to 305 minus 273, and that comes out to be T2 is equal to 32 degrees Celsius. Okay, so the exit temperature that we needed to find out is 32 degrees Celsius. Now let's match this our answer with the given option. So we can see here option A is the correct choice. To get more information on first law for steady state, steady flow process, you can refer to the NPTEL course on concepts of thermodynamics by Professor Suman Chakravarti of the Department of Mechanical Engineering at IIT Kharagpur.